So, today we will discuss the strong and weak convergence in the non-linear space. We have seen that in calculus there are so many ways of defining the convergence, like we have ordinary convergence of a sequence, then conditional convergent sequence, absolute convergence of the sequence, and uniform convergence. This concept we have gone through in case of the calculus. Ordinary convergence simply x n converges to x means mod of x n minus h goes to 0. Conditional, all a series is ordinary convergent. Okay. Conditionally convergence, when the series is convergent, but its absolute term is not convergent, conditionally convergent of the series, and absolutely convergent when the each term is replaced by the absolute value and the series is convergent, and uniform convergence when the sequence of the functions are there defined over a certain domain. Then we say that sequence of the function converges uniformly. Okay. It means the epsilon should not depend on the point. Mod of f n x minus f m x should remain less than epsilon, whatever f n f x and f z, whatever x and z may be. Okay. Inside that, it should not depend, epsilon should not depend on the point, but in case of the convergence of the points is important. Okay. So, these are the different various concepts of the convergence in case of the calculus. The same type of concepts we also have in functional analysis. Okay. In case of the norm space, we also have these concepts, but apart from this, one more concept which we have in case of the norm space as a weak and strong convergence, because every norm space one can find out the dual of it, okay, dual space of this, and then once you get the dual space, the f belongs to the dual set of all bounded linear functionals. The convergence in with respect to that involving the bounded linear functionals plays an important role in the development. So, that convergence termed as a weak convergence, okay, and the convergence in the norm we term as a strong convergence. Convergence in norm we mean that if a sequence x n belongs to a norm space x t and we say the x n converges, it means there must be some point x available in the x such that the difference between x n and x under the norm should be or go to 0 as n tends to infinity. That is the convergence norm. Okay. So, we define the first the strong convergence as the convergence in norm. Strong convergence means a sequence x n in a norm space x norm in a norm space x norm is said to be strongly convergent or we can also say convergence in norm. In the norm, if there exists or there is an x belonging to capital X such that the norm of this x n minus x as n tends to infinity is 0. Then such a sequence we say the sequence x n is a strongly convergent in M. we denote this as by saying x n converges to x in this norm, means it is strongly convergent. Okay? That is what, and x is called and x is called a strong limit of the sequence x n, a strong limit of the sequence x n. Okay. The concept of the weak convergence is as follows: a sequence x n in a normed space, in a normed space x norm is said to be strong weakly convergent if there is an x belongs to capital X such that for every f belongs to its dual, this is the dual space of x, dual space of x. For every f belongs to x dash, limit of this f of x n as n tends to infinity is nothing but f x, and it is denoted as by saying x n converges to x weakly. Okay. So, this x n converges to x weakly, and x is called weak limit of the sequence x. So, basically what is the meaning of the weak convergence is that x n is a points in x, this is in the norm space. So, a vector quantity when f is the functional defined on x, a linear bounded linear functional. So, when we say x n converges to x means the corresponding sequence of scalars, and scalars is obtained as by taking the image of x n under f. So, f of x n becomes a scalar when the sequence of scalars converges. Okay. Then such a sequence x n we say it is a weakly convergent. Okay. And this limit f of x n equal to f x as n tends to must hold good for all f belongs to x dash. Okay. Then only we say the sequence x n converges to x weakly, means its image under each bounded linear functional goes to f x corresponding f of x. Okay. Then we say that our sequence of scalars goes to this. Okay. Now, this weak convergence various application in analysis, and most like a differentiation equation, general theory of differential equations and other. We require certain lemmas to go in deep the results on weak convergence. So, first lemma is that is on the weak convergence. The proof of these results on the weak convergence requires rigorously the application of uniform boundedness theorem. So, this gives you results where the uniform boundedness theorem is used, okay, or is an application of uniform boundedness theorem to analysis problem. Okay. What is the weak this lemma? Let x n be a weakly convergent sequence, a weakly convergent sequence, weakly convergent sequence in a norm space X norm. Say weakly convergent and say suppose this sequence goes to X weakly. Okay. X n is a weakly convergent sequence. Now, it means there must be some point x available in X such that x n converges to X weakly, all f of x n goes to f x for every f. Then the following results holds. The weak limit x of the sequence x n is unique. Just like in case of a ordinary convergence, if a sequence x n converges to x, alpha n converges to alpha, then this limit alpha will be unique. Means we cannot take a sequence converging to a two different limit points, then we say the sequence does not converge. So, just like in sequence of a scalar, the limit is unique. Similarly, in case of this weak convergence or weak limit is unique. Every subsequence of x n converges weakly to x. Okay. Just like in an ordinary sequence of a scalar, if a sequence converges, then all of its subsequences will also converge. So, similarly, here also it will converge weakly. And third is the sequence of norm, the sequence of norms is bounded. Okay. The proof of this is what is the weak limit x of x n is unique. So, given that x n converges to x weakly, it means f of x n goes to f x for every f belongs to its dual, is it not? This is the dual space. Now, f of x n is a scalar quantity. Okay. So, basically what you are getting is that this sequence will go to f x scalar. Now, suppose a weak limit is not the same. What is given is we wanted weak limit of x is unique. So, suppose the weak limit x is not unique. It means there exists some other y, that is there exists y such that x n also converges to y weakly. Okay. So, that is the meaning is the f of x n goes to f y for every y for every f belongs to its dual, is it not? Is the case? Now, f x n goes to f x for every f n x goes to f y for f. We wanted the x equal to y. So, let us consider f x minus f y. F is a bounded linear functional. So, we can write f of x minus y as f is linear. Okay. But f of x minus y, f x equal to f y is given. So, this must be 0. Okay. And this is 0 for every f belongs to its dual space. Okay. So, what it shows is that f of x minus y is 0 for every f belongs to its dual. Is it clear now? Because we have assumed that f x this is x y it is 0, okay. Because the reason is, it should I write it, because f of x n is a sequence of scalars, is a sequence of scalars, is it not? And sequence of a scalar cannot have a two different limits. So, this implies the limiting point f x must be equal to f y, is it not? Because x n converges to x means f of x n goes to f x. But what is f of x n? It is a sequence of scalars, and we are assuming that this x n is not unique. So, we are assuming another y, but basically by definition of weak convergence, f image of x n under f will go to f of y. Since f of x n is a sequence of scalar, therefore, its limiting value f x and f y will not be different if it is therefore, it is equal. So, once they are equal, it will be 0. Okay. So, this is 0 for every f belongs to x. Now, from here we can say x minus y equal to 0. Why? Okay. If this is true for every f, then this must be 0 for every f, and this implies x equal to y, unique time. Why it is? No, there is a lemma. This is by the following result. What is the result? Let me just see. The result is, or is corollary of this Hahn-Banach theorem. The corollary of the Hahn-Banach theorem says, for every, the result is for every x in a norm space x norm, we have norm of x equal to supremum of mod f x over norm f, f belongs to x dash, and f is not equal to 0. Hence, if x naught is such that f of x naught is 0 for all f belongs to its dual, then x naught will be 0. So, because of this result, we can say that f of x minus y is 0 for every implies x minus y is 0. Now, this result follows, from Hahn-Banach theorem. How does it follow from Hahn-Banach? What is Hahn-Banach theorem? Hahn-Banach theorem says that if x be a say norm space, and x naught, if I picked up any point non-zero point here, then corresponding to this f naught, we can find a f naught, f or f naught, such that f naught x naught is 1. F naught x naught is x naught. What is that? That what was the Hahn-Banach theorem is? This was the Hahn-Banach theorem. Let x be a norm space and x naught be a non-zero element of it, then there exists a bounded linear functional f delta. This is a bounded, there exists a bounded linear functional f delta on x such that f delta x naught is norm of x naught and norm of f delta is 1. Is it not? This is what we call it the Hahn-Banach theorem in case of the norm space. Let x be a norm space and x naught be a non-zero point in this, then there exists a bounded linear function f delta such that image of this x naught and f delta is norm of x naught and the norm of this is 1. So, using this we can say the norm of x, we wanted to show the, so start with this supremum mod f x over norm f, okay, when f belongs to the dual and f is not equal to 0. Obviously, this will be greater than equal to this particular f delta. So, this is greater than equal to f delta x, is it not, f delta x over norm of f delta, but x is fixed. So, norm f delta we can find out if such f delta where norm is 1. So, this is equal to f delta x, is it not, but f delta x is equal to norm of x. So, this is norm of x. Okay. So, this part is greater than equal to norm of x, but mod of f x, this is equal to what? This is mod of f x is less than equal to what? Norm of f into norm of x. So, this implies mod f x over norm of f, supremum is taken over all f belongs to this, f is not equal to 0, will be remain less than equal to norm x. So, combine these two, we get this lemma is true, that A is true, A follows. Is it clear? Now, if A is true, then what it says is x naught is such that f of x naught is 0 for all x, then x naught must be 0. Now, if this part is 0 for all f, then obviously the supremum will be 0. So, obviously norm of x naught will be 0. So, it follows immediately, and norm x naught 0 implies x naught must be 0 because it is a norm, clear. So, this result, the f of x minus y equal to 0 implies x minus y 0 follows from this result. Is it okay? Clear? Now, let us see the second part of this. So, part A is true, second part proof of this, every subsequent x n converges weakly to the same limit x. Now, this follows here, since x n converges to x weakly, okay, this is given. So, this implies that f of x n converges to f x for every f belongs to x dash, but f of x n, this is a convergent sequence of a scalar, and every convergent sequence is scalar, the subsequence is to converge to the same limit. So, all of its subsequences will converge to the same limit point, clear. Hence, this follows, clear. The C part, what it says, that sequence norm of x n is bounded, the sequence norm of x n is bounded. Okay. To show the sequence norm of x n is bounded. So, let us start with this. Given x n converges to x weakly, so this implies f of x n will converge to f x for every f belongs to the dual. It means the sequence f x n is a convergent sequence. Okay. Every convergent sequence is bounded sequence of scalars. So, it is bounded. it is bounded. Therefore, there exists some C, therefore, there exists a C, constant C, which depends on f such that mod of f of x n, this will remain less than equal to constant C depend on n for all n. Is it okay? This C will not depend on n, it will depend on f, because f changes, the corresponding constant will change. Okay. So, we get this one. Now, let C be the mapping from x to x double dash, which sent x to g of x. Okay. This is a canonical mapping, which we have already discussed. Okay. So, the canonical mapping defined by g x f equal to f of x, is it not? And it is linear, this was already shown to be linear, is it not? And bounded also, clear? Linear and bounded, this we have seen it. Okay. So, let us consider, so therefore, g of x n f, mod of this is equal to f of x n, is it not? Therefore, mod of this thing, mod of g of x n f is equal to mod of f of x n, but mod of x n is less than equal to C f. So, this is less than equal to C f for every f belongs to the dual. It means that this sequence mod of g x n f, this is the sequence, is a bounded sequence for every f belongs to the dual. So, this operator g of x n is a bounded operator pointwise, it is pointwise bounded, because g is defined on x dash and g of x n f is less than equal to C for every f, is it not? And C depends on f. So, it is a pointwise bounded theorem. Now, since g x n is defined from what? X dash, is it not? This is defined from x dash to g of x n to double. No, x dash, it is an element of x double dash, but basically the domain will be g n of f will be the point in real. Okay, that is what. So, it is defined on the real or C, is it not? Now, this will be a complete norm space, whether x is complete or not, x is not, but dual space will always be complete. So, a sequence of the operator is defined on a Banach space x, is it not? X to y, this is, and this one R and C. So, this will be what is our uniform boundedness theorem? The uniform boundedness theorem says, says that if T n be a sequence of operators from x to y, where x is a Banach space, y may or may not be a Banach space, just norm space, such that norm of T n x, this is a bounded sequence for every x belongs to x, then the sequence of the norm is bounded. Okay. Now, G n is defined on X dash, which is a complete space, a complete norm space, Banach space, clear, and G is bounded pointwise. So, according to the Banach uniform boundedness theorem, we say norm of G n will be bounded. Okay. So, from here using the canonical mapping concept, and uniform boundedness theorem, we say that norm of this sequence G of x n, this is bounded. Is it okay? Bounded. And what is the norm, canonical mapping? When G of x n is there, then norm of G x n is equal to norm of x n, which is the same as norm of x n by canonical mappings, because that operator which we define, is it not? So, is also bounded. Is it okay now? So, hence the theorem is proved. So, this proves the C, because we want the norm of x n to be bounded. Is it okay? So, this comes. Now, in a general norm space, we have seen the concept of the weak convergence and strong convergence. Why do not we have this concept in a real or complex, when x reduced to the real set of earlier number or set of complex number, or in general a finite dimensional space? The thing is, in case of the finite dimensional space, the weak convergence and strong convergence are equivalent concept. Means strong will imply weak and weak will imply strong. But if x is not a finite dimensional space, then these two concept differs. Strong always implies the weak, but weak may not implies the strong convergence. Okay. So, we will see that in case of the finite dimensional space, the strong convergence and weak convergence are identical. Okay. So, that is the next target of origin. So, we have the theorem. Let x n be a sequence in a norm space x norm, norm space norm. Okay. Then the following result hold: strong convergence implies weak convergence. With the same limit, with the same limit. The converse of A is not generally true. And C part is, if the dimension of x is finite, then weak convergence implies strong convergence. Okay. Let us see the proof of it. Strong convergence always implies the weak convergence. So, it is given x n converges to S strongly. Strongly means under this norm, that is norm of x n minus x goes to 0 as n tends to infinity. We want the weak convergence. So, start with this mod of f x n minus f x. If I prove that this goes to 0 agenter, then it is okay. Now, f is a bounded linear functional. So, this can be written as this form. Further, f is bounded. So, we can say this is less than equal to norm f, norm x n minus x, as f is bounded. Is it not? This is true for all f belongs to, for every f belongs to the dual. Okay. Now, x n goes to x is given. So, will it not tends to 0 as n tends to infinity, because this is a bounded thing and this goes to 0. So, f x n converges to a, therefore, f x n converges to x weakly, okay, because this is true for every x. Now, part B, the converse of this is not true in general. It means in a general norm space, strong convergence, weak convergence need not implies the strong convergence. So, we have to take a counter example where the sequence converges weakly, but it is not the strongly. Okay. So, I take the x to be a Hilbert space. What is a? Because Hilbert space, there are also a norm space, but is it not? Every Hilbert space is a norm okay, the Hilbert space, yes, inner product we can introduce the norm, is an inner product, norm of x is the inner product x x under root, clear. So, we can find out the, so let us take the Hilbert space and let E n be an orthonormal sequence in the in a Hilbert space H, in a Hilbert space H. Okay. Now, it is given that weakly convergent. Okay. So, let us consider now, let f is an element belongs to the dual, that is f is a bounded linear functional on a Hilbert space H. So, its representation by Rietz's theorem. So, by Rietz's theorem, representation theorem, every bounded linear functional f can be represented in terms of the inner product. So, by bounded linear function, every bounded linear functional A can be represented in terms of the inner product x z, where z is uniquely determined by f and norm of f equal to norm of z. Is it not? X belongs to H and f is this. This is by Rietz's representation theorem. So, we get f of E n. F of E n will be inner product of E n z. Is it clear? This is okay. Now, use the Bessel's inequality. Bessel's inequality. Okay. What the Bessel's inequality says is, the Bessel's inequality is that sigma of the inner product x n by n mod square is less than equal to sigma norm of x into norm of y. Is it not? That is what is a Bessel's inequality. Yeah, let E k be a orthonormal sequence in inner product space. Then for every x belongs to x, that is, if E n be a E k be orthonormal sequence in an inner product space x, then for every x belonging to capital X, the sigma of inner product modulus of inner product x e k whole square k is equal to 1 to infinity is bounded by norm of x square. This is what inner product the Bessel's inequality says. So, apply the Bessel's inequality here. What we get from there is, therefore, sigma k equal to 1 to n is equal to n is equal to 1 to infinity modulus of inner product of E n z. Okay. This whole square is dominated by norm of z square, but this is finite. So, this series converges. So, the series converges absolutely, is it not? Series converges. Therefore, the nth term must go to 0. So, inner product of E and z, this thing must go to 0 as n tends to infinity. But what is this? Is it not the f of E n goes to 0 as n tends to infinity? Okay. Clear? So, E n converges to 0 weakly, because this is true for every f belongs to H dash dual of this. Is it okay? So, E n converges to 0 weakly, but E n not converge, but E n does not converge strongly to 0. Because norm of E n minus E m whole square, this is inner product E n minus E n minus E m, and this will be 2. So, it is not Cauchy. Okay? Clear? Therefore, it will not converge. Is it okay or not? So, E n does not go to 0 strongly. Clear? Therefore, every weak convergence need not implies the strong convergence. So, that is the. Now, third part, the proof of this, if dimension of this is finite, then weak convergence and strong convergence are the same. Okay. So, let the dimension of x be n and the basis elements be, and let n E 1 E 2 E n be the basis elements of x. Okay. Basis element for x. Let x n comma x are the element of x. So, x n can be expressed in a linear combination of E 1 E 2 n. So, there exist scalars alpha 1 n, alpha 2 n, alpha n n such that the linear combination of this is x n. Is it okay? Okay. Oh, this dimension and this dimension. So, we are taking x n, but here x n is coming. So, let the dimension of this, okay, let it be m, then it is okay. Clear? Otherwise, confusion will go. Yeah, m. Is it okay? Yeah. Now, x can also be written as alpha 1 E 1, alpha 2 E 2 and alpha n E n in terms of the basis element. Now, it is given x n x m converges to x strongly, then obviously, x m will converge to x weakly. It is by result A, every strong convergence implies weakly. So, now let x m converges to x weakly. We want this converge to this. So, that is the given as f of x n goes to f x for every f belongs to the dual of it. For every f belongs to dual. Now, in particular the f 1 f 2 f say f 1 f 2 Fk's or Fn's, these are also the element of X dash, where F I X E K, F I E K is the canonical delta K, which is 1 if I is equal to K, otherwise 0, is it not? And F1, F2, Fn, these are the dual bases. In particular, these are the dual bases, and this F1, F2, Fn will form dual bases. So, these are the elements of X dash, is it not? So, in particular, this F1, F2, Fn will also be the dual. Okay. Now, this will be in so what is the image of this X n under F j will be equal to alpha j n X m, is it not? Because you apply the F j. So, F j E j will be 1 and rest will be 0. So, alpha j m, and this is true for all. And what is the F j x is alpha j. Okay. Now, it is given F j x m converges to F j x. This is given because so this implies alpha j m goes to alpha j, okay, as m tends to infinity, is it not? Therefore, norm of x m minus x, consider this, which is equal to norm of sigma j equal to 1 to n alpha j m minus alpha j E j. Okay. Now, this will remain less than equal to sigma alpha j mod of this into norm of E j, is it not? Now, sigma j equal to 1 norm of E j is finite and this part goes to 0. So, this will go to 0, this is finite. So, entire thing will go to 0 as m tends to infinity. Therefore, x m will converge to x under this norm strongly. Okay. So, x m converges to x weakly implies S m converges to x strongly, and that is proved. So, in case of the finite dimensional, this is true. Okay. But there are example of the infinite. It does not mean that infinite dimensional the weak convergent never implies a strong. No, there are examples of a infinite dimensional norm space L1 has a property that weak convergence also implies strong convergence. Okay. There are other space also parallel to L1 where this is true, but in general it is not true. In general infinite dimension weak convergence need not imply strong convergence. Okay. In a infinite dimensional norm space. Okay. But there are certain space even infinite dimensional where it comes, but we require the proof of this thoroughly. Okay. So, just this example I have given in this. Now, there are research is going on to find out the criteria, the sufficient condition when the sequence converges weakly under that norm, because always the infinite dimensional space is not necessarily the weak convergence implies a strong, but we can obtain certain condition, we can impose a restriction on these sequences, so that that sequence will imply the weak convergence is okay, or weak convergence, what is the criteria for. Okay. So, these results just I will tell the examples in a Hilbert space, x n converges to x weakly if and only if inner product x n z goes to x z for all z in the space. Okay. I think this follows immediately by Riesz representation theorem, follows from Riesz representation theorem. Why? Because f of x n is when x n converges to the, because x n converges to x weakly means f of x n goes to f x for every f belongs to the dual. Okay. But f of x n by Riesz theorem, this is the inner product of x n z, this will go to the x z by Riesz. Okay. Therefore, it will follow. In case of the space L P, the criteria is in the space L P, where 1 is less than p less than infinity, we have x n converges to x weakly if and only if the sequence norm of x n is bounded. Okay. And second part is for every fixed j, we have x I j n goes to x I j as n tends to infinity, okay, where x n is a sequence x I j n and x is a sequence x I j. Okay. B is for every fixed j, x I j n converges to x I j. It means, if f is a point in L P dash, L P dash dual of L P dash is L Q. Okay. So, f belongs to the dual of this, then f of x n will go to f x by means of this weak convergence. Now, this will converge weakly if the coordinate wise convergence of x n is also there. X j n, because j you fix, it means x j 1 n will go to x j 1, x j 2 n will go to x j 2 n. So, if x n converges to x coordinate wise as well as the norm x n is bounded, then the sequence will converge weakly. Okay. So, we are not going for detail in the proof of this, but these are the results. So, this type of the work continues, means you take the space, find out the sufficient condition, because these are basically the necessary and sufficient both conditions. Sometimes we are unable to get both time. So, we get only the sufficient part, again, because it is required the condition when the sequence converges weakly, and that is. Thank you very much.